guess is correct, he earns some points, and that makes him more, that makes this place more engaging, of course, but also helps us understand whether user knows about this fragrance, this is new, or this is already known to him, and based on that, some other fragrances can be also um, offered. And metaverse can also have multiple avatarized bots intended for different purposes. For example, we may have a bot which can give you a walkthrough of the place. We can have a bot which can help you selecting the products, or we can have a bot which can help you persuade about a product. So what you see here as one example in which this avatar, this is a virtual bot. She is talking to the user and helping her uh, shortlist some perfumes, and also even offering her to select some perfume, uh, customize it, and even create her own formulation and create an NFT out of it, which is an important part of metaverse context. When we talk about metaverse, we often talk about the creator economy, which is about having and owning your own stuff, and that is going to be one of the major economic factor or the business model which will keep these platforms running. And we already see some success stories of creator economy from TikToks of the world, in which people create their own videos. But what we can imagine in the context of metaverse, that the creation can the creation part can be expanded just beyond the videos, audio, but also other types of objects. So moving on to the next slide, um, I hope it gave you a glimpse of what the metaverse looks like. Uh, let's understand the potentials which metaverse has. So the transformation metaverse will bring is definitely inevitable. For example, Unity CEO has predicted that AR VR headset will be as common as game console by 2030. And what you see here is a graph of the affordability of devices as per the unit of visual immersion, which is called UVI, which is calculated using the field of view resolution refresh rate of the hardware devices which is used. And as you can see here, that they are actually gradually becoming much more affordable, and also in future we will see these devices will be much more lightweight and easy to handle, and people will start owning pretty much like they own a game console or even a phone. Next slide, please. So, not just this, early market signs are also very positive. The creator economy is real and will grow significantly, allowing user to take a stake in the development of the metaverse. New metaverse platforms like Sandbox, which are missing many essential functionalities, are signing hundreds of partnership. And it's not just the game companies which is actually growing the usage of metaverse and becoming social network. BMW is designing and building factories in metaverse and then operating them. Accenture itself has leveraged virtual places for onboarding its employees, around 150,000 new joiners, in which they all onboarded on Allspace environment, which has been hosted, and they could meet and greet, and everything has happened on that platform. Let's have a next slide, please. So let's have a look at the metaverse value chain. Metaverse value chain then consists of these 3 to 4 steps. Infrastructure is one which is about the core network which is going to be provided by the metaverse. Hardware is, for example, 5G is going to be playing a very crucial role, because the requirement of any metaverse in experiences will be about high bandwidth, low latency type of scenarios. Hardware, we will see the emergence of new and new devices. Even the multisensory devices are going to come. Governance is going to be very important because we need to really set the rules and policies about the metaverse, which are still not very clear. We might have heard about a news of actually a molestation happens through the avatars in the metaverse environment. How do we handle those scenarios are still not clear. Spatial computing is an important element because metaverse is about spatial experience, so how we can improve it is another important facet of metaverse. Creator economy, I have talked about, that is going to be playing an important element again in value chain. Discovery is about how do we even know that different type of metaverse experiences exist and how we can support them. And the last and but not the least is the experience platforms are going to emerge a lot. Next slide, please. So, having said all this, let's have a look at the role what AI will play in metaverse. So, just for the simplicity, I have actually identified five to six important facets which are often being talked about in metaverse and what role it would play. So, in my view, AI is a domain that offers a bunch of techniques and methods or tools that can be used in number of scenarios, be it optimization, enhancement, interaction, or to address hardware limitations. So, the different aspects of metaverse will find different AI techniques more suitable, and let's have a holistic view of this thing what we see here. And we will just drill deeper on only two aspects given the time duration, because AI is having a broad impact on each element, each of these elements. So I will just go through each one of these very quickly and then hand it over to the rest of the speaker for handling the two important topics here. Next slide, please. So, first thing is the role of NLP. NLP plays a vital role in metaverse as it can enable natural interactions through intelligent virtual assistants, for example, chatbot. And we have seen that NLP or the NLU involves things like speech to text, text to speech, conversation design, voice branding, etc. And they often employ techniques like RNN, LSTM, CNN, and the similar type of techniques are going to be quite useful in the context of metaverse. Another important element is that the natural language generation will not be only limited to the voice and text, but will also be about the animations of the avatars at the right moment, at the right time. So we have to see that. Second thing is that metaverse is about a multi-user system in which we will have the people's avatar as well as the pure virtual avatar. So a multi-party conversation is going to be an essential requirement for any metaverse requirement, and that is where conversational technology needs to advance more. Just to give you a teaser, what you see here in the left hand side is a virtual influencer. It is India's first virtual influencer, and she is a bot, and she has millions of followers on Instagram. And she keeps on posting about her things, and what you can imagine that maybe these texts are auto generated, and and her actions and body language can also be auto generated, and all those can be made possible with AI. Next slide, please. Computer vision. So, this is again another very important area that will have profound impact on metaverse experiences. AI is required in metaverse in multiple contexts. For example, rendering. AI can address limitations of present rendering engines by optimizing the content which is delivered to the user. For example, AI can actually predict based on the eye fixation or the head movement or the gaze that which area the user is going to look at, and then enhance only that particular area rather than focusing on everything. AI can offer a lot of creative AI tools for people to create their content and monetize on that, because otherwise creating stuff requires a knowledge of a particular platforms and tools, but AI can really democratize that. AI can actually help in authenticating the people uh, understand. So basically, right now, the authentication is mostly the biometric based on the face. We can even think about an authentication which actually based on not just the face but your gestures and but the way you behave, and maybe after a few times you can just be authenticated in the environment that this is real you. Next slide, please. Coming to the another important aspect, which is about the interfaces. So far, what we have seen, and that is right now the case, is that most of the immersive popular interfaces in the context of metaverse is VR headset with a controller. However, many technology companies are now paying attention to the neural interfaces, and that's where again AI needs to mature. A lot of things are already happening, but it's still a lot of things have to really happen in future also. So for example, EEG signals are being interpreted in brain computer interface applications, but they are not accurate enough. They require wet electrodes instead of dry electrodes, and probably with better algorithms we can be able to understand the signals better or filter better and then use that meaningfully as another type of interface with metaverse applications. Then we have the other simulation devices to simulate smell, touch, taste. Right now, all these peripheral devices are need to be programmed, and they need to be calibrated uh, as per their specification. So AI can actually do that calibration and all those things automatically, and understand the limitations of the device to make a more immersive and engaging experience. Next slide, please. So digital twin is another important area, and digital twin is actually a real digital representation of the real world entities. It offers capabilities such as monitoring, visualization, analyzing, etc. So if we look at the digital twin, they are the center where the physical world and the virtual world interact with IoT connection. For example, we can imagine a technician can maneuver 3D representation of a complex system at multiple levels, and that 3D representation can come from a scanning technology to scan it. So what you see here as a picture is the scanned experience of a living room, in which you can actually have a walkthrough of the space, and you can actually overlay a lot of information on top of that uh, to troubleshoot if some device is not happening, etc. So right now the challenges in this space is that the scanning technology as well as the proper generation of the 3D model, there is a gap, and AI can fill it. So for example, scanning happens with the laser beams and it creates a point cloud, and then after that you create point cloud is one type of 3D representation. Then you have to create a mesh in order to experience it in metaverse. Now in that process a lot of fidelity is lost, or some information is missing. AI can actually fill up that gap and create a proper complete mesh model which can be realistically used in metaverse. Next slide, please. Blockchain is another important element in metaverse to provide security, privacy, and authenticity. And AI can again play a major role, and it's already being used in other contexts where blockchain is being used to understand the cyber attacks and classifying them and then addressing them better. And I think most of them are going to be relevant here also. Next slide, please. And last piece is networking. And networking, I think we might have, if we have worked in this area, we might have seen that AI and ML algorithm have been used to do an intelligent routing based on the traffic patterns and all those things. And maybe when the 5G and in future 6G comes up, we may need to employ much more intelligent algorithms which also take into account the different types of channel bandwidths required for content like 3D video or voice, and how that can be multiplexed properly with with the help of such algorithm. So I've just given a broad overview of everything. As you can see that AI can have a profound impact and all the aspects of it. But for this tutorial, we are going to just focus on the two elements, the computer vision and natural language interfaces, how they are going to enhance the natural interaction or interaction with the user through better NLP techniques and avatar technologies, and how computer vision is going to assist people to and empower them with creativity tools and enhance their spaces. So I just hand it over to Nitish.
Thank you, Alpna. So now we are going to talk about immersive content generation in Metaverse using AI. Next slide. So procedural content generation is very important or core technology behind any content generation, especially in kind of a metaverse scenario or gaming scenario. So PCC is defined as like method of content generation using algorithms. That algorithms can be from a mathematical function, statistical method, or even these days with artificial intelligence. So, like if you see in the right hand side example, this is an example of content generation. So we are giving some rules like generate rooms. So it's just generating some rectangular boxes. When we are giving another command of generating maze, it's drawing some thick lines in between those boxes. So these existing PCG methods, they are some rule-based or grammar-based or search-based methods, and they are applied to generate either some content, the or some maps or some characters. In gaming scenario, they are also used to define different levels for different users, and sometimes also the characters and the textures of those characters. So if we see on broadly, the PC is mainly used for enhancing the scene, basically like from a low quality scene to a high quality scene, and updating a scene dynamically. That is like adding or removing any object. So as you saw in the right hand side example, that we added new rooms, we added new mazes, and then we are joining them. So we are basically creating different scenes and also the creativity tool for the users. So we will be talking in details about scene enhancement and creativity tools in this session. Next slide. So this is the PCZ with AI, where scene enhancement with AI means generating a photorealistic 3D view from a very low fidelity image, which can be a voxel diagram, or it can be just a block level diagram. The second example with the creativity tools with 3D data generation is about generating a 3D model altogether. So we have already seen that using rules, we can generate some rectangular boxes. Those are already some predefined images or predefined uh, set of geometries. But how we can generate a very random object? So as you can see in this example on the right hand side, that all these are like generated 3D image, the 3D models from just text. So basically, a Koji wearing a red Santa hat, you won't see that in real life. But with AI, this kind of content also can be generated. So we will talk in details about these two, the technical blocks and how that happen. Next slide. So the scene enhancement, this is a work from AI where uh, it it generates a like a photorealistic 3D view from the Minecraft blocks data. So this algorithm basically is a combination of 3D volumetric renderer as well as 2D space renderer. So it starts with first generating a 2D image and then combining those 2D images to generate a 3D view. So to generate a 2D image, as you can see in the the left hand side, this architecture, it starts with voxel world. So basically, voxel world is a 3D representation where each voxel, or you can say like a cubical block, represents a particular class. Like the green color one represents the trees, the blue color represents the water, or the brown color represents the ground. So from these voxel representations, a segmentation map is created, as you can see in the bottom. Segmentation map is also something similar but in 2D view. It also where each pixel represent a different class, like the blue color represents the water body, the green represents the trees. From this segmentation map, the first part is to create a photorealistic 2D image. And that for that, we use a state-of-the-art model called SPADE, that is semantic image synthesis with especially adaptive normalization. So this technique basically generates a realistic 2D image from semantic layout. And then we also use the like GAN based model and CNN renderer to further make this image more realistic and more in line with the voxel world. So similarly, different views are generated and then they are combined to generate a 3D scene. So next slide, please. The second one was the creativity tools. So here comes the 3D content generation. Here you can imagine the users who are entering the metaverse and they wants to generate something, uh, not only some predefined objects but also very creative or new object, either through a sketch or through text, or even like from another 3D they want to view it in another 3D representation. So generally, this using recent development in the 3D deep learning, we can generate images from point cloud or meshes. So these are the different 3D representations, and they have their own limitations and their own advantages. In metaverse, mostly meshes are used because they are comparatively of very better quality, and they captures a lot of informations about the 3D models. Next slide, please. So we are going to talk about the two examples. One is generating 3D models from text, and other is generating 3D models from sketch. And this is the first one. So this paper is Pointy, which is a very latest work on generating 3D model from text data. It goes through two models basically. First is uh, for text to image generation, and then second is image to a point cloud generation. So in the first part, like you can see in the right hand side architecture, it takes a part of the text like a quasi, and then using another architecture called glide, which is used with the basically a guided text guided approach for image generation. It generates a view of this koji. The another part of the text, like the red Santa head, that is also added, and that is another view is generated for that text part. And then this kind of text inputs are combined, and always also the images which are generated, they are also diffused to generate basically a point cloud which captures a koji wearing a red Santa hat. So this is how you can see like the creativity of users, and that's where the as we discussed in the previous session about creator economy. So how the users can enter and they can create their own content with just few clicks with AI technology. So next slide, please. This is another example of basically generating 3D models from Sketch. So this is a work from Accenture Labs. Here we have developed an ensemble model which first generates 2D to 2.5D, which is basically a sketch only, but with the depth and normal information of that sketch. And then it generates a 3D model from that 2.5D representation using another technique called implicit decoder, which is used to generate very high quality 3D model from this 2.5D representation. There is another state of the art network which is being used recently a lot, that is differential volumetric rendering, or commonly known as DVR, which learns not only the shape but also the texture representation of the input sketch or image, and it generates a 3D model along with the texture. So here you can think like you are generating a lot of furnitures in, let's say you are in a retail or a furniture store where you can generate a lot of furniture with the textures of your choice in just few click. So now, next slide, please. So Avino will now talk you about how we can add textures or styles or different patterns using 3D style transfer techniques.
Thanks, Nitish. So far we have seen how we can generate 3D content with using images, sketches, or text. Can we stylize 3D scene with different colors, textures, or patterns? This will add another interesting aspect to 3D content creation, basically. So we can imagine stylizing the scene within the metaverse, indoor scenes within the metaverse, and different objects within that environment, basically. So how to achieve that? So this is one of the work, basically style transfer for indoor 3D scene reconstruction. So as you can see over here, we have a 3D mesh, okay, of this indoor scene, and then you have a style image, basically. Okay, and this style basically you are applying onto this 3D mesh, and and the output you can see on the right. So this entire area gets painted in the form of this style. Okay, as you can see, there are different outputs. The bottom is basically, this is the image, the referential image, or you can say the style image. And this is not actually the image, basically. So this is the 3D mesh which you can see over here. So different 3D meshes, and you have a style, and you can apply that style onto that 3D scene, and you can generate different patterns. So that's the idea of this work. Coming to the next. This is another interesting work. I feel this is a more practical approach, where you have a input 3D mesh, okay, and uh, language as it means this input text as a language, basically input text which you are providing, that okay, you want to have a marble wall, means wall of marble type, cabinet wooden type, counter steel type, and that input you're passing it through the model. So the model basically takes two inputs. One is the 3D mesh, this input colored 3D mesh, and another is the user's input, the user's textual input, basically. And then you can see the output. So we have a wall of marble type, and the cabinet, wooden cabinet, basically. So we can imagine that okay, we have an entire 3D scene. We can segment different areas, and we can apply textures or some different styles based on the user's input. So this is a more practical and controlled approach. So how we can achieve it? So what are the technologies to achieve this kind of a solution? So you might have heard about 2D style transfer. It's very popular. Like you have seen like lot of artistic images it being generated using some kind of a style which is applied on the content, and you get a altogether new stylized image. So I'll give you just a basic idea of how 2D style transfer approach works. So uh, in any style transfer techniques, we have one content. So here it's a content image. I'm talking about 2D, and you have a style image. Okay, and the style you are applying it on the content without losing the functionality, without losing the structure or pattern, basically over here in the content image. So we can imagine we have a kind of a networks, let's say CNN networks like Inception, VGG, ResNet, or even the more recent architecture. So passing the content image and the style image through different layers, extracting the features at different layers. So content loss is being, and we measure then the content loss, basically. So the content loss and style loss is being measured, and then we compute total loss, which is a weighted sum of alpha and beta. Alpha and beta basically content weights and style weights, and then overall we optimize this total loss through the back propagation. So that's the basic idea, and there are a lot more advancements in this particular approach. So a better loss techniques, Laplacian smoothing and all, to improve the quality of the output. So I'm just talking about the basics over here. So at Accenture Labs, so how we can take this 2D to 3D? So that's what we have developed at Accenture Labs. So 4 ways to achieve 3D style transfer. So 3D style merge, theme transfer, shape transfer, and 3D texture transfer. I'll discuss this in the next slide. So I'll play this video to explain what these different 3D style transfer looks like. So in 3D style merge, what we are doing, we have two 3D objects, and then we segment it and then merge it. I'll be discussing even more detail. In theme transfer, we have a 3D object having some kind of a texture, what you can see on the this one, and then we are merging with the style pattern, generating an altogether new pattern onto that. So that's the 3D transfer, theme transfer. Then we have a 3D texture transfer. So you have a content and you have a style. So style, you can see here, it's a 3D engravings basically, not the 2D pattern. And you're generating an altogether new styles in this. And finally, the shape transfer. Here you are blending the two 3D shapes to generate a new stylized output, which you can see over here. So talking about the first one, 3D style merge. So what we do over here is we first take two, means any, when we are talking about style transfer, we have always two things. One is the style object, another is the content object. So you can see over here these two objects basically. So first in this one, what we do, we first perform segmentation. We can use any 3D mesh segmentation models. So we are targeting the mesh models basically, a kind of a representation for 3D object. So we first perform segmentation of the content object and the style object. So we have different components as you can see over here. Now to before merging, what we do over here, to we have to preserve the functionality of the content object. So we should know that, okay, when we are kind of a merging this object basically and placing it onto another, it should be compatible. So we are measuring the compatibility. As you can see that compatibility matrix, that which parts can be merged with other another parts basically over here. So we have used Siamese based approach to find out the compatibility between the parts. And then finally, we are performing a merge operation using the pose estimation based approach, or even you can use any heuristic or geometric based approaches to merge that one. Moving on. So in theme transfer, this is pretty straightforward, a bit much similar to what we have seen in 2D one. So we have a 3D model. We extract the textures basically of the 3D model, and we also have a style, pass it through CNN model. So again, CNN can be your any inception model or resonate models which we can use, or recent ones. Then you measure the content loss and the style loss, optimize this loss, and generate the stylized image, what you can see over here. And then you perform UV mapping and put it on the 3D object. That's the idea. So you can see the output on the right, basically, on the different verses. Then we have a 3D texture. Why it's coming blurred? Okay, fine. So then you can see the 3D texture transfer. So the idea over here, you can see this is the content and this is the style. And this style is a 3D pattern, basically, not the 2D what we have seen in the earlier slide, more like engraving, and that kind of a thing which you want to apply it on the content, and you get a new stylized type. As you can see here also, this is another work, deep geometric texture synthesis, where you have this content and different styles you can see is being applied, this texture is being applied on this. So I'll give you a very basic idea of this, how the 3D texture transfer works. So first we extract local geometric features. It's hard to see actually over here, but as you can imagine that this is a object. Okay, so first we extract local geometric features per triangular face basically. So considering this is a triangular one, triangular mesh, so per face you are extracting that local geometric features, and then you pass it through a series of face convolutions, okay, to learn deep features. And the final convolution layer will be a output like a displacement vector per triangular matrix. So how much displacement which you will be doing for each vertices basically. So that's you're predicting over here. Now coming to 3D shape transfer, so as you can see what the idea is like, you have a content, you have a style, you can generate the stylized shape. That this is another work. They both are 2022 work actually. So here also we are taking one content style, and you can see the stylized shape is somewhat in between the content and the style. And here also you can see that there is a curve and that you are applying onto this. So how it works. So we have several components like encoder, style encoder, content encoder, discriminator, uh, then fusion model basically that I'll talk, and the generator. So the idea is we pass this source object and the content target object, basically the style object, through content and style encoder to get their embeddings. So once we get the embeddings, we pass it through a fusion model, and the fusion model is going to generate the latent code. Okay, that generally we use, if you have heard about any GAN based model, we use some kind of latent information. Sometimes we take a noise. So here we are getting an embedding of both encode content and style embedding, and thus we pass it through generator to generate the stylized shape, and then we pass it through discriminator to see whether the generated outputs are real or fake. uh, So we can imagine that having such kind of a tools can facilitate in generating different 3D designs at scale, and it can also assist the designers in their design process basically. So even a lot of metaverse platforms, you go over there and you can create different contents using these kind of techniques basically. So what's the next basically? So if you see 3D, if you have seen 3D shape transfer, lot of work basically focus on the point cloud. So point cloud is one kind of a representation of 3D model. So maybe we can explore on like how we can going to stylize the mesh basically. So when we're talking about 3D shape transfer, how mesh data can be created using that 3D shape transfer. So that's, and we can also focus on kind of improving the existing algorithms of 3D texture transfer, which is a very recent work, I would say. So that's the idea of 3D style transfer. So from here I'll hand over to Roshni.
Thanks, Abhinav. Hi, everyone. We can go to the next slide. So, if you think of intelligent interaction in the metaverse, you can really think of it as two parts to it. We can go to the next slide. Yeah, you can really think of it as two parts to it. One is you have the virtual humans. Now, you can think of the virtual humans if you've played in any gaming platform as these AI bots walking around, sort of pre-scripted. But virtual humans, what we are thinking of is much more sophisticated in the fact that it can actually be designed to look realistic, but also act and speak in a very human-like manner. And the second is the interactive avatar. So the avatar is really our representation in the metaverse. And right now, other than just relaying maybe what we have typed in or spoken, it should really be able to reflect our emotions, gestures, and maybe other aspects of our personality within the metaverse environment. Now, if you think of these two paths, right, they really will pull in together a lot of the research work that is within multimodal, including speech, text, video, and will also require a lot of sophisticated reasoning and understanding capabilities. Next slide, please. So as a way to kind of holistically think about what is needed to bring together this virtual human, right, we'd like to start, maybe you can start with the left, top middle left, where we talk about history, where this virtual human actually has its own past stories, its past interactions, also with the current interactive avatar or the current user within the metaverse, right, and has its sort of belief system within it, right. The second could be something where it is able to have or construct knowledge on deep knowledge on a certain topic, and have a mechanism to constantly update that knowledge around that. The third is really about embodiment. So we saw these photorealistic images in the previous slide, but it's also about reflecting a personality, being able to gesture, being able to show sort of emotions, and other aspects. The fourth is really interesting, very much within the metaverse environment, because we want these virtual agents or virtual bots that we interact with. They will have certain clear goals, right? So if it is a bot, and if you go back to the video that Alpana played earlier, you had these virtual agents which maybe are like your perfume assistants or shopping assistants, right? And their goal is really to kind of help you get what you need and maybe even persuade you into getting certain things. You could also think of the virtual influencers that we talked about earlier, where a virtual human completely embodying a virtual influencer could actually help kind of influence the user within the metaverse environment. The fifth is really kind of the crux of many of the work that is happening right now, because it's a understanding your natural language understanding generation, sophisticated reasoning capabilities, but it's also some of the most subtle things, which is a little difficult, is understanding a bit of the user's verbal non-verbal cues, knowing when the user's really paused, because you'll see in certain cases, even now, you still have to press the start and stop button, right, when you're speaking into an agent. So knowing when the user's pause, when the user's unable to complete their sentence, when the user's trying to barge in, etc. So all those subtleties kind of come in this aspect. Next slide, please. So, within this conversation, within the virtual human and within conversational AI itself, what we try to do is we try to look at some of the more today's technology, some of the more practical aspects, and we look at also some of the key research areas and challenges which will really be extremely useful within this metaverse environment. Next slide, please. So just for fun, we thought we'd ask ChatGPT, since it's becoming now an embodiment of chatbots all over, right? What would how would chatbots be used in the metaverse? And you can see it's got quite a nice elaborate answer with some very valid points over there, right? And so if you were to really extrapolate some of the points here, you'd see that a, of course, chatbots, virtual humans, let's say they're synonymous right now, because of course virtual humans requires a little more, a lot more than that. But let's say as synonymous, first thing they would do is maybe support or assist you within the metaverse, right? So understand your request, being able to demonstrate knowledge and kind of guide you, right? Which is a little more in the frame of what chatbots kind of do today as well. The second is a little more sophisticated, because you're thinking of chatbots not just as service agents to say, okay, what can I do for you? Let me do this. Or as we also call task oriented agents, but they're really bringing in aspects of collaboration. And through collaboration, they can recommend things to you based on your personality or your persona. They can persuade or negotiate with you. And the third is really more around demonstrating a strong kind of personality, showing empathy, etc., where we start to delve into what people feel is more human like, right? Even the engaginess and being able to maybe chit chat and things like that, right? Takes you from task oriented and goes into more of the human realm. Next slide, please. So first, I'll just take you through a little bit on what chatbot technologies exist today from the whole range. We'll talk a little bit about language models, which is very practical way in which chatbots are being used. And the third, we'll talk about other aspects within chatbots like knowledge, collaboration, empathy, which kind of even delves into some of the very interesting research areas and research directions that are being taken today. Next slide, please. So as you can see, right, if you take chatbots maybe from the very first early well-known, which is called Ravenclaw Olympus, to what we've talked about today already, which is ChatGPT, you'll see that it's really starting to evolve from multiple components, multiple specialized component systems, to trying to bring a lot of things into a single model. Right now, you can see that even today, if you have your automatic speech recognition (ASR) models and your TTS, which is text to speech, these two are separate models. Whereas when you delve into the text processing aspect, you today's commercial systems have actually broken it down into first natural language understanding, dialogue management, which sort of manages the interaction, and finally the natural language generation part. And you'll see largely that NLU is a fairly sophisticated, where we use language models, but to a large extent the generation capabilities are template based, and the dialogue capabilities tend to be sort of flow based, where you have to sort of build in those elaborate interactions. Of course, at the other end, GPT ChatGPT and some of its counterparts are, generating a lot of interest because you can sort of train it with well-known prompts and kind of use feedback to kind of make it more holistic and bringing these three aspects together. So that's really where things are headed. Um, Next slide, please. So I want to talk about three ways in which language models are being used. The first, maybe most common, is basically fine-tuning existing language models like BERT. The second is what can be done with one-shot learning, where you don't do any training but use a language model as is to give you the right response. And the last is prompt engineering, which is really in the realm of the large language models like GPT-3, GPT-Neo, etc. Next slide, please. So the first one I want to talk about is the intent slot dialogue act training. So this is really about taking a language model and for a particular intent. So intent is basically the request, the specific request made by the user, understanding that and assigning a category to it. So basically a classification. And you can see here for a general language model for a particular intent type. The first one example here being balance inquiry. You can see that there are a few variations of the query you provide. Similarly, for another thing called check booking, you can kind of give those variation segments. And this is today how a lot of chatbots are sort of trained. You can extend it to dialogue act, which is a classification, but although intent usually is domain specific, dialogue act can be thought of as domain agnostic. So it'd be kind of a request, a feedback, a question, and those kind of abstract classifications. On the right, you can quickly see how entities are sort of trained. And basically an entity is a word or noun phrase which is a kind of important for a particular intent. You can see slightly in pink, you can see examples like Boston, Denver, Pittsburgh, etc., which are the entities that are tagged. And then you have other things like in slightish greenish gray, you have morning, which is the time of day. And then you've got things like cheapest, which is a constraint on the intent, etc. Next slide, please. So in one shot learning is really about taking an existing model, passing it an existing intent, and either a single label or a set of labels, and the model actually returning, based on a semantic relationship between these two, actually returning a confidence score of how likely that classification is right, or how likely that intent is correct. And it has been used, a particular example provided here called TARS, it's actually been used well to understand sentiment and to understand certain kinds of intents, named entity recognition, etc. One very interesting area where one-shot learning is can be commercially used is in the unknown intent detection space, where a lot of chatbots, once they're deployed, things evolve when a user asks a lot of questions which it was not initially trained for. So being able to identify that it is not its existing intent, which itself is a challenge, but secondly, being able to kind of come up with possible intents that could be valid for it. Next slide, please. Another interesting thing we talked about is prompt engineering. So prompt engineering is really about taking a very large language model like GPT-3, providing a context as an input, and then sending it a query where it will actually respond based on that initial context that you had set. So in the example on the left, what you can see is that you give it a very simple context where you say, okay, it's a chatbot designed to help you with technology, and you have to respond appropriately to the user's text. And here you can see the conversation that has been had, right? Green is the response by the chatbot based on the context. You can also see that if you change the context in a certain way, so instead of saying, you're designed to talk about technology, but you're actually designed to talk like an alien, for example. So in a sense, you're kind of embedding some sort of a personality to this. You can see that there's definitely a different response, not only when you ask a generic question, like what can you help me with? So it gives you a appropriate answer, but even in the follow-up question, sort of sticks to that context that is given. Now, prompts can be of this example, but you can also give not only context, but you can give sample question and answers as examples or as templatized examples, and that will give it even more information to sort of give you that response. Next slide, please. So now that we talked about a little on what things are practically being used, we want to talk a little bit about where the research domain is sort of heading, right? So you can see this particular chart on the left. This is from BlenderBot, and you can see it's a very interesting generative chat, right? Because this chat not only depicts personality, it has opinions, it has some favorite. Um, favorite songs, etc., favorite kind of music, etc., like that. Now, although this looks very well constructed, there are certain challenges that it is kind of showcasing over here. One challenge is the fact that it's not always going to be consistent, because today you ask it its favorite song, it'll give you one answer. Tomorrow you ask another favorite song, it may give another answer. The second is, if you ask it for things that require a specific understanding or domain understanding, it's not clear what sort of answer it might give. All these issues being highlighted in the paper, and all these issues being reflected in large language models itself, right? So one of the ways to do that is actually have a mechanism where the chat model can actually go to an external knowledge source, whether it's Wikipedia or some other knowledge graph, be able to extract the responses and give that answer back. That is obviously one aspect, and that will also help with the in memory sort of where it will not be inconsistent. Other aspects are, one is the hallucination of facts, which will also help if there is this external knowledge. So hallucination basically means it'll just make up something that is not right. Third, of course, is the safety. So you cannot guarantee that the chatbot will be non-toxic or will not give you some sort of biased response. That is sort of still a very active area of research. The third thing I want to highlight is this very interesting example. Sorry, the previous slide itself. Yeah, this very interesting example here is where you can use common sense graphs. So you have existing common sense graphs like ConceptNet. You have the transformers based on these common sense graphs. Like you have, for example, ConceptNet, Atomic, and then you have Comet, which is sort of trained on them. And you can see that you can actually use this general knowledge to give better and more contextual answers to the recipient. Just invite you see this example where someone asks flowers, and common sense understanding helps map the fact that rose is a type of flower, rose is also a symbol of love, and then you can kind of respond appropriately to the person. Next slide, please. Yeah. So one aspect I want to talk about is this aspect of persuasion, which is something we think will be very relevant in the metaverse environment, because that actually really brings in collaboration, negotiation, persuasion, all these sort of related traits here. And one thing I want to point out is that currently chatbots are more like service agents, right? You give them some requirements, and it tries to process that and give you its best answer. Or it's like a constraint matching engine. And this is the conversation you really see on the left. But genuinely, if as a shopping assistant you really want to help your users, you have to extend that a little bit, right? So, for example, on the left here, it cannot meet all the requirements of the user and just says, okay, sorry, there's no such phone for you, right? Whereas realistically, what you need to do is you need to kind of update your goals. That is one part, because users given maybe 10 constraints, you have to sort of select the most important constraints from the user. You have to give some suggestions to the user, say, okay, I cannot meet all these constraints, but this is something I can do. That is, I can suggest A, or I can suggest B based on some of these more important aspects. So try to pick those things. And the third could really be about persuasion, right? Picking out the most important aspects and also persuading the users on other criteria, because you might also say, like, you know what, this is a great, if the user's hesitant, you'd say this is a great phone because it's maybe the most popular model that was made this year, or after all, it's a Nokia. I mean, you can definitely trust a Nokia, right? There's different ways, or you could have an emotional persuasion. Look how beautiful this phone is, or it's my favorite phone, which is more like a personal story or a personal strategy. So the different ways that you can bring about to kind of maybe close this deal, right? And in a sense, it ties into our clear goals. Then very quickly, just want to point out here what we try to put together is it now becomes not only about intent and slot filling, and understanding multimodal data from uploading images, etc., but also understands your sentiment or emotion, also incorporates a persuasion strategy within it. You can go to the next slide, please. So here you can just see other examples of this where it really talks about the importance of the strategy. So it's not about just throwing things at you, but subtly putting things across in a way that will sort of influence you. Or, as you can see in the first example, rather than bringing up a rejection, it actually sweetens the deal a bit, so you can do that. And on the right, you can see the importance of various built-in strategies and kind of relating them together, choosing between them, etc. Next slide, please. So a couple of things remaining here. One is if you talk about persona, then persona is basically understanding the user's view of the world, what they like and dislike, and sort of relating a conversation to that. This is still a very active area, and what I've put here is two data sets which kind of have been put together and are trained and can be used to train chatbots to sort of understand this persona and reflect the responses accordingly. Next slide, please. The last is sort of very interesting, is, related to empathy. So, empathy is really two parts. One is understanding the user's affect, so not just emotion, but overall affect in a multimodal fashion. So, if you can see the model here on the left, it takes into account not only audio features, that is maybe like the tonality, etc. of it, but the actual facial expressions of the user and other aspects of the video. So that's more like the situation depicted in the video to kind of come together and give you a range of valence and arousal, right? Which really gives you the range of emotion of the user. The second is, okay, once you understand the emotion of the user, instead of directly giving responses, you actually tailor that effectively to the to the emotion. And it's not just like, a one-to-one mapping of, okay, you're sad, you say I'm sorry, but you kind of have ways of responding that take the conversation forward, which is really delve into um, aspects of empathy, like acknowledging, sympathizing, agreeing, and others. This is something that has been very actively pursued when you come to these mental health bots, which will also make their way into the metaverse environment, but also sort of things like nursing bots, etc., where you kind of have to deal um, in the medical domain with users. So you can go to the next slide. Here are just some commercial solutions that we've sort of put together, and they're not exhaustive, but just want to point out that, for example, Yellow.ai and Rasa are things that you can just go and sort of configure. Rasa's open source, and they kind of you train models similar to what we talked about in terms of intent, entities, and providing the training data. Yellow.ai also have one-shot learning. Amelia and Soul Machines are a little more closed in that, so they have their own proprietary framework, but they have very sophisticated avatars that are part of that, and they actually demonstrate through their videos and through their work a lot of empathy with those chatbots. Um, next slide, please. So with that, I'll stop here and I'll pass it over to my colleague Nitish to talk about the interactive avatar.
Thanks, Roshni. So now we just have we got a quick glimpse of what all technology are there in conversation, how the people are interacting, what they should take into consideration when building such bots. But this is another important aspect of how this can be applied to the avatars who are there in the virtual environment. So that is going to be very important part, like the interactive avatar, that how these avatars will interact in metaverse. So next slide. So if we see these avatars, this started with the 3D digital avatar when people were interacting with the so we already know that the market of this 3D the market of this avatar is growing a lot with expected cumulative annual growth of around 46%. And these avatars in the metaverse has become more relevant because people want to join those platforms with more interaction and more experiences, let it be retail or education or training. So these avatars, which are as of now, which are defined in this a lot of applications, they have there are some limitations, and that's where the researchers are working to bring up more way of interaction. So these avatars have limited animations, limited gestures, and not very personalized experience. And that's where the AI, along with the other technology like neurotech or smart wearables, can bring novel solutions. So next slide, please. So when we talk about the 3D avatars, actually there are two types of avatars. One is like the user avatar. So if I am entering the metaverse platform as a user, so I want to, how do we want to see my avatar in metaverse? So that is the user avatar. Second is the bot in metaverse. So we are talking about like sales representative or the trainers, uh, or like even the educators who are joining the metaverse, and they are kind of as a bot, and they are kind of doing the conversations to either give you the sales the descriptions, or either to educate you about some topic. So if we see this, there are a lot of tools which are there in market, like to create these avatars, like Ready Player Me, Deep Motion, Avatar SDK. So if you see the right hand side, this is a like avatar from Decentraland. So there are some predefined set of animations. So these are some of the limitations I'm going to point out, and also I will discuss in more details how this can be solved using AI. So these are some predefined gestures which you can do in the decentralized environment with your user avatar, and that limits you to not to have multiple gestures. And the gestures are common or generic for all the users who are entering the metaverse application. So Deep Motion has tried to build some solutions, gesture replication, and but they can see in the right hand side bottom image that uh, basically with the geometric approach they fail to replicate the hand movement properly. And when we talk about the bot, we saw that as Roshni has pointed out, a lot of important aspect like emotions, empathy. So those things are missing when in these bots in metaverse. So they should have more dynamic interactions, more they should have the capability of showing emotional and empathy angle. Yeah, next slide please. So that's where the future is, like we need a more human like avatar, more interactive avatar, which can show a real time emotion and gesture through multimodal input that can be either feedback from neuro sensors or from smart variables. And then that's where AI is going to bring up this more realistic avatars. Next slide please. So these are some of the technology that we just kind of pointed out. So when we talk about avatar generation, the first thing is the photo to 3D. Basically, from your human face or your geometry or whatever the like you want to see yourself. So we can generate a 3D model from that photo. Second part is the text to 3D, where along with the image, you are adding the text also to add either emotions or some gestures. You can manipulate the generated 3D avatar with the text input. The third is audio to face. So basically, avatar is not only about the body, but also the way you are moving your lips or you are moving your facial expressions. So that is being captured when you are talking, when you are doing some conversations. Your words should be reflected on the face. So that is the audio to face. So the another aspect is emotion. So along with the audio, like if you are happy or you are sad, those emotions should be reflected on the avatars. So let's say we talked about the persuasion strategy. So the avatar should persuade and show some emotions at different point to make more personal connect with the users. The gesture is the another aspect is gesture, that is also very important, because the gesture is very important part of conversation when you are in the same example, when you are trying to talk to a customer, your gestures are very important, and that gesture should be more dynamic, it should not be static. The another is full body avatar. So this is a like we talk about face, we talked about the gestures, but as a full body avatar, this is a combinations of all this, like as a as a complete, your persona is being transferred to the avatar. So the way you talk, the way you show your gestures, the way you show your emotions, that are being captured and animated on those avatars. So next slide please. So these are some of the latest work, as you can see, like these are all from the last years. So and this technology basically are helping in to solve these problems. So I will go in technical details of some of them to show how we approach for this avatar generation using AI. Next slide please. So as you can see in the right hand side, text to 3D avatar, sorry, go back. As you can see in the right hand side, the text to 3D avatar. So basically this is a text and image guided avatar generation and manipulation. So here the first the text embedding is taken, and then from the text embedding your either the emotions or the your gestures that are being captured. So in this example, like you can say like a picture of a happy human, so happy is a keyword. So and with the image basically this is like the avatar is generated, and then this emotion is being like reflected back to that avatar. So using a model called differentiable renderer, which basically renders this text embedding on those avatar or generated avatar. Second is like audio to face. So this is you can see this is using a cross modality. So basically, your input is in the form of of an audio signal, and that audio signal along with your emotional state is passed to the network to generate a 3D model, a 3D face model, which basically can will change according to your audio signals. So audio signals is basically a kind of in a raw data, and this the 3D model has a lot of facial key points. So basically, this network is predicting the location of those key points with the input audio signals. So with each word, like how much, like how the way you talk and the way you change your facial gestures or expressions, that is being captured on this 3D face model. And emotional aspect is going to add a new angle to it, because along with the conversations, let's say you are smiling while talking or you are feeling annoyed, so those things are being captured and being replicated on those the 3D face. The other is the gesture animation. This is, if you see in the left hand side image, this is where we are also talking about multi-user interaction or multi-users gestures and recognition and animation on the avatar. So here there are two approaches. One is called top-down approach, where from the input image, if there are multiple users, so each of them each of them are the users are cropped, their 3D pose are estimated, and then we align it in the 3D world. So that is a top-down approach. In a bottom-up approach, from this input image, we create a 3D pose network from estimating their depth, estimating their like relative location or standing from each other, and then we create their from their body part, basically their pose estimation in the 3D world. We and then generate a 3D multi-person view. So this kind of solution can be really useful when we are talking about the multiple users entering in the shopping platform. We saw in the example our first like part of the session, where in the metaverse, the multiple users are interacting in the retail store, and they are talking about or purchasing any product. About, like for example, the perfume case was there. The last is like the full body avatar. So here, this is in a network which generates a from your full body. It's generating a 3D model. So here, the one-to-one correspondence with your 2D image and your 3D model is done, and then this neural renderer basically renders each point, and basically it tracks the movement of each point in the this video or the input image, and then it maps to the generated 3D avatar. So next slide, please. So I will take you to more details about these two state-of-the-art models. The first, on the the left-hand side, is about this basically a 3D GAN model for full body generation from an input image. So this is where all this research is started. So this is an input image. So first, the input your full body is segmented, and then using some geometric approach, your 3D model is constructed. This uses another GAN-based model called InferGAN, basically to get inference for your back texture or back image. So this is an ensemble model which uses like geometric as well as GAN approach to generate a full textured mesh from the single input image. I will also post a collab link for the same, which you can try to upload your image and get your 3D model. The right hand side, which you see the example of, I mean, can you click once? No, go back. Sorry. So this is a video actually the in the right hand side which takes a multiple views as an input, and it generate a complete animatable 3D mesh model. So here you can see like your videos are captured to and your that is being replicated to this 3D model. So in the right hand side, if you see, there is a skeleton is created which is in avatar technology that is called armature or rig. So from this armature or rig and your 2D and your video, there is a one-to-one correspondence as I was talking about, like your hand movement, your leg movement, and your head movement. And so all those gestures are captured, and then the 3D model is created along with those gestures. So this you can see, imagine like once someone entering the metaverse, and their hand movement, their way of talking, their expressions are exactly the same uh, as the like the real human. So you will feel very much like this will be very personalized avatar, and you will also feel very connected. So this uses a concept of neural radiance field. Basically, so the first part is generation of single view of frame, and then using neural radiance field, it's generating or completing a 3D view from those set of images. Next slide, please. So I will, in the interest of time, I will just post the link of this collab, which you can try for your avatar creation. So next slide. So I would like to conclude with these opportunities and about like we saw that how AI can be used in multiple ways to build a multi-sensory, multi-user, and multimodal metaverse, where along with the visual and natural interface, you can also uh, experience with multiple senses like haptics, neurotech, aroma simulation, taste simulation, and how the multiple users can interact and do like their experience can be more immersive through the multimodal. It can be in form of conversations or gestures or emotions. We already saw example of this in the first slide, the right hand side picture, if you remember it. This was about the retail experience of which was capturing this metaverse experience. So I would like to conclude with this. Any questions? Thank you, everyone.
Yeah, let me know if you have any questions. Speakers are here to answer your question.
How does content generation 3D? Thank you for this nice presentation, sir.
Yeah,
First, my question is that how does 3D content generation can influence in additive manufacturing, like 3D printing and all,
can influencing. Sorry.
in developing that additive manufacturing technology, that 3D printing and all, how it can develop? And my second question is that is there any way to check the practical, I mean, limitations? Like suppose a veneer when is applied on a wall, there's many practical limitations are there that we cannot directly expect what is actually we are seeing in the metaverse. So is there any way we can actually incorporate that also?
Yeah, so there are a lot of work currently, if you see, which is kind of improving the sterilization, or if you are applying to, you're talking about the wall. So there are some works basically which we can share with you, which is kind of improving. But as I was mentioning that a lot to explore in this area. This is a new area. The 3D world is kind of evolving, and this is a kind of a new area. So. I think a lot of research would come which will handle the cons which you are talking about. Okay, like the if we remember the first one where we are painting the entire scene altogether. That is a very recent work, 2022 work actually. And then you have seen the next work where we are kind of segmenting the area and then we are kind of applying. So improvement is being done by the researchers on top what we have currently. Coming to your first question, so 3D model generation basically in for manufacturing, I think it's pretty much there. There are many works basically uh, which is being targeted just for the 3D manufacturing itself. Okay.
Yeah, I would just like to add something here. So the AI generated 3D models, generally, so far what we have seen, they are high poly, and then there are also holes in it, and many times they are not manufacturing ready, as uh, as your question was. So, but there are pipelines available through which you can actually, for example, there are hole filling algorithms through which you can create a solid model from a mesh model, basically, which can be then 3D printable. So anything which we need to manufacture has some extra constraints on the 3D model, and there are independent tools which can be stitched together to create that type of model from the AI generated model. And then still, I would say that complete end-to-end pipeline and chains which can work for all types of models are not there, and that's again one of the areas where AI can actually help complete that gap, because yeah, I mean, also another area which we can call is as 3D model for manufacturing, 3D generation for manufacturing.
So I had a question in the part where you mentioned that 3D models, the voxels to photorealistic images. So my question here was that how do you sync between different photorealistic views of the same model? And what kind of what level of segmentation do you expect? For example, I guess the example which showed, it showed trees, right? But it could be, for example, humans. So it could be, what level of segmentation do you expect? Front, back, facial expressions, etc.
Nitish, you want to take this question?
Yeah, yeah. So actually, that depends on the details. So as much details are there in terms of segmentation, like the objects which are there, like in terms of trees or the land or the water body. So the generated 3D output is going to be something like based on the input. So if the inputs are not that detailed, the output will be little less less quality. But there are some generalization also that you can see, like if all these landmarks are like even the input is are marked as a land, but you can see like a gradient in the land in the generated realistic scene. So we need more, like the more details for the segmentation, but with the less details also it can generalize to create or generate a realistic view. But again, it depends on the like there are going to be some limitation for sure, with like if there are some labels which are not like completely out of the context, that it will not be generalized to that. But if there are some the input are in line with the objects which are already labeled or which are part of the training set, let it be land or water body or trees or plants or small plants, bigger plants, so that will be captured even if it's not very detailed segmented. I hope I answered your question.
So the one another part of the question was, for example, in the same 3D model, photorealistic views were generated. So for the same area, I mean, the views can be captured from different
Yeah.
angles, right? So what is like, did you try seeing how the views were in sync? Like, was generating slightly different photorealistic images for the same view? Because the labels are quite generic, right?
So basically, the question is like, you have a multiple views, right? Okay, so
Hmm.
whether they were in sync or not. I mean, how you have accomplished that. So they have a different sync altogether. So how you manage that basically?
Okay, so this is a concept called neural radiance build. Basically, it generates a kind of a space for all the input images, and with whatever the input images, let's say you are giving input images in three viewpoints, it will try to generalize with those viewpoints. So there are there as you, I think you wanted to ask that if there's a back of the image that is not there as an input, how will we generalize it to it? So because the model has seen from the different view angles that how in the training part, basically with the different viewpoints, what is the relative or translation of the same image in different viewpoints. Then so based on the input, it will try to generalize it to other viewpoints, because that's what the neural network learns as a part of radiance field. So it kind of generate basically a field or a space, and then it will try to generalize or fit whatever the inputs are there, and what will be the translation from those inputs to the next one. So the 3D world is created by translation of each of those frames. So even if some frames are missing, it will generate based on the learning.
Does that answer the question? Okay.
So you talked about differentiable volumetric rendering.
Yeah.
So my question is, how is differentiable volumetric rendering different from neural radiance fields? So radiance fields are also volumetric fields, right?
Yes.
So
Yes.
yeah. So what is the difference then?
So differential volumetric rendering is another aspect. Like in radiance scale, it's considered different viewpoints. In differential volumetric rendering, it also tried to basically generate the 3D model considering the textures as well as so there is a concept called occupancy networks, which basically uses the 3D model as like generates a 3D model with a probabilistic approach that whether that point is there in the 3D space or not. So for a given generation, for a given input image or like colored image or a sketch, it will generate a 3D view, and the final prediction is going to be in terms of whether that particular point is there or not. So it can be generalized to multiple scales. So both are actually different ways of generation. In neural radiance field, it was a set of 2D images and it's trying to generate. And in differential volumetric rendering, it's only single image. From that image, it's trying to generate. So algorithmically, they are different because the DVR is using a concept of occupancy networks, and radiance field is using another like concept for neural renderer. So that is the approach wise both are different.
Oh, so my question is like in neural radiance field, we cast a ray into the scene and we accumulate the gradients. It's
Yes.
just volumetric, right? So we
Yeah.
cast.
Yeah.
So in occupancy, there is you're saying that whether that field is occupied. So it's just a binary occupancy function, 0 and 1.
Yes, it's a binary occupancy function at the end that whether that is there or not. Yeah.
So for binary occupancy function, like how does texture uh, appear in binary occupancy function? I can
So
understand in neutral radiance fields we have colors and density. We can
mhm,
learn these
mhm.
colors and density. In
So
binary
that is
occupancy, it's 0 and 1. How do we learn texture?
yeah. So that is another part like that. I so in DVR actually it's not a like a single model. It's an ensemble model where the like first part is generation and the second part is like the texture application. So texture also carries with the like the input. So in the binary, like we are talking about the like just whether that that point is there in this space or not. But there is like the another part of it where this which texture or which the texture is there or not in that like where we are trying to predict the texture for that point. So that's how the texture is also applied in DVR.
So you're saying that we have yet another model that learns the texture,
Yes,
occupancy.
yes, it's a
And
part of yeah, it's a part of DVR. Like DVR is like so in occupancy network is one subset of DVR network. Texture is replication is another subset.
so this texture is like, is it based on this BRDFs or it's like completely different? Like,
No, it's a completely different. It's just applied uh,
okay,
through like
so
yeah.
so one final question. So you talked
Mhm.
about differentiable rendering. So
Yes.
for your work, I'd like to know what differentiable renderer did you use?
So actually, I talked about state of the art models of TVR. Like we have not, we worked. The other work that I talked about was sketch to mesh. That's the work from Accenture Labs that we have done to generate a sketch, to generate 3D model from single view sketch. So there we have used basically a two ensemble model. First was from sketch to 2.5D, another was from 2.5 to 3D. So in 2.5 to 3D, we used a first encoder that basically to extract the features from the different 2D 2.5D views, and then we use a like implicit decoder basically to de- to again find that probabilistic approach to predict whether that point is there in the 3D model or not, and then we generated that 3D model.
So, where in your pipeline does the differentiable renderer fit in?
Differential limit is another state of the art. That's what I just think, that was another state of the art that is used to generate. That was a similar or
Not,
extension of
so,
similar our work.
so you did not use it. You're just giving an
No,
example.
no, we are, yeah, just giving the example.
Okay, okay. So, so and what one final question is like, so how is this 2.5D that you are talking about? These points, how is that different from the SLAM and structure from motion thing that people use?
So these are different representations actually. So 2.5D captures like it's an image only, but along with the image representation basically captures the depth and the normal information. When we talk
Yeah.
about SLAM, there are already different images, and different images along with the different images, they keeps tracks of like relative localizations of relative uh, like pictures or different frames. So theirs are just a different representation in a way, how they are being captured in the informations are the same, like the depth information, the normal informations, but the representations are different. In SLAM, it's like set of images, or in 2.5D, it's the pixel value of these single images that captures the depth.
So when you talk about 2.5T, like what exactly are you talking about? It's an image, right? It's
It's an
a
image, but
RGB
it's an
image.
image, yeah, where each pixel value basically represents some depth information also.
Okay, so it also has a depth information.
Depth information, yeah.
So and and that is generated using what, like how are you generating that?
So from 2D input, we can generate 2.5D because the 2D input is a single sketch. So we don't have depth information in a single sketch. So there is a architecture that I just shown in the image that is called multi-view decoder. So that multi-view decoder is not only generating. So basically, it's an encoder decoder architecture that takes single view sketch and it generates multiple views of 2.5D. So it's kind of decoding not only or generating not only the multiple views but also with the depth information.
So it's not from single view.
No, input is the single view. The generation, so input is single view, but the model is, that's what the model is learning through. Uh, that's the learning part. That from the training data set, it learns that okay, for this given input image, what all possible 2.5Ds are there, and that was the model that the generative model learns and try to generate for the test image, that if you pass a single sketch, it will generate multiple 2.5D. So a sketch has no depth information. Input sketch is single view sketch without depth information.
Okay, okay, thank you. Your work is really interesting. So
Thank
it's
you so
been
much.
nice to know more about your work. Thank you.
Thank you.
Okay, so thank you to all the speakers. And yeah, there's one more. Yeah, sure.
So thanks for this session. So there are a lot of technologies which are being used to create this metaverse experience. So I wanted to know what are the success metrics. So how do I measure the success of this technology? So do we have some metrics that we can track? So, the whole metaverse experience. So how do I know that we are able to do something with it? So
Okay, so who would like to take this one? So metrics as such means,
So
yeah, ma'am, you want to take it?
no, I just want to add there, like so we like the metrics, we can talk about different components, like we talk about conversation, we talk about generation. Overall, if we see in the as a metaverse, complete metaverse, uh, like like that's very like broad field to generalize. So
That's
No,
interesting. Actually,
that
maybe
that
we can have a metrics by next year. Maybe we can think on it. Yeah.
Yeah, I mean that's right. I was just adding that just to add to what Nitish said, that each aspect will have its own metric, uh, and this field is a bit new to have an overall metric. But one thing I feel could be a metric is the overall engageness within the metaverse, right? So people are spending time within what you have constructed, and they're achieving their goals. Which is again going to be based on user feedback itself, that can in some sense formulate a metric. But yeah, there is no formal definition that I've seen right now.
Thank you.
Okay, so yeah, thank you to all the speakers. So we'll have the lunch in the ground floor cafeteria. But before that, I think the attendees can go to the main hall, VMCC. I think there's some announcement or something like that. Yeah.